Hello, today we are going to discuss about tree data structure. Already all of you know what is a data structure is. It is a way of organizing data so that it is easier for you to access the data and remove the data. So any data structure we can classify it into two types, linear and non-linear. So linear types includes stack, linked list, queue and different variations of these things, and non-linear it is tree, graph, etc. So we are going to deal with tree today. Why that name tree comes? Because it has some similarity with the actual tree. So imagine a tree in an upside down. So you can see here a tree will be having root and will be having different branches, and branches will be generating from different intersections like this, and then there will be leaf. So root I am calling as a node, all these different intersection for each branch I am calling as a node, and then also the leaf is also a node. So a tree definition is actually a tree is a finite set of one or more nodes such that there is a specially designated node called root, and the remaining nodes are partitioned into disjoint sets like T1, T2, Tn, and we call all these T1, T2, Tn are subtrees of the root. Okay. So actually a tree will be represented by using a hierarchical way like this. That is why it is non-linear. And now we are going to discuss about different terminologies of a tree. So of course I already told you the first node on top we are representing as what? Root. Now here you can see a tree is drawn here. A node will be there, we are calling it as a root, and then so many branches are there, so intersection part is there, those part also I am calling as a node, and then finally we have leaf. Now first terminology here we are discussing is about what is the degree of a node. So degree of a node is the number of subtrees of that node. So consider this root. This is a node and it has two subtrees. So degree for it is 2. Take this node and it has 3 subtrees generating from it. So its degree is 3. And for leaf there is no subtrees generating, so d equal to 0. So I can say that a node with degree 0 is a leaf. Okay, now what is the degree of the tree? Degree of the tree is actually the largest degree in that any of the node. So that I am calling as degree of the tree. So degree of the tree is what? 3 now. Now children of the same parents are called siblings. So here you can consider a parent. This is a parent node and it has 2 children, and these 2 are sibling of it. Similarly for this case these 2 nodes are sibling of it. And few more terminologies are there. Next is ancestor of a node. So ancestors of a node are all the nodes along the path from root to that particular node. For example, ancestor for this node, all the node from root to that node, they are all ancestors of that particular node. Next we have descendant of a node. Descendant of a node is all the nodes which are under its subtrees. So it is very easy. Now another terminology is level of a tree. So here we are assuming that root is at level 1 and the next level is 2, next level is 3, etc., and finally next level is 4. So you can see some variations in this definition. Different books will be referring different way, but if you are following a particular assumption, all the theorems will be based on it. Okay, now tree representation. Here there are three ways you can represent a tree. So we will be discussing about three ways. One is list representation, the next one is array representation, finally we have linked representation. So list representation of a tree, here consider this particular tree, and you can see A is a root node and it has three children, B, C and D, and B has two children, E and F, and in that E has two children, K and L, F doesn't have any children, and C is having only one child, and D is have three children, H, I, J, and out of which H has M as a child, and I and J doesn't have any children. So you can see here A, that is the root node, and we have B, C and D. Three nodes are there. So B contains its subtree, so the entire thing will be represented like this. So B, C, D. Now inside B it has two children. What is that? E and F, and E has again two children, K and L. C has only one child, that is G, and D has three children, H, I, J, and H has one child, that is M. So this is what the linked representation of a list representation of a tree. Now next we will move on to a tree with a degree 2 or maximum degree 2, that we are calling as a binary tree. So binary tree is a finite set of nodes that is either empty or consists of a root and has two disjoint binary tree called left subtree and right subtree. But we can also say that rather than general definition, a binary tree will be having at most two children. So at most two children, it means it can have a single child, it can have degree 0 child and degree 1 child and degree 2 child. Okay, so we can check binary tree examples. So here this is a binary tree. It has a left subtree, there is no right subtree. The degree of A is 1 and degree of B is 0. Similarly, this is another binary tree, but left child is missing, and it's A, the degree is 1, B degree is 0. And here you can see only left child is there. Such type of tree we used to say left skewed. It is skewed to the left. And now here we have a binary tree. A has two child and degree of A is 2. B has again two child, degree of B is 2. C has two child, F and G, degree of C is 2. Likewise it goes. So these are all examples of binary tree. Now we will discuss about different properties of binary trees. First property is maximum number of nodes on level I of a binary tree is 2 raised to I minus 1, where I greater than or equal to 1. What it is talking about is, take this binary tree, level of this is what? 1 here, level of this is 2 and this is 3, and it is talking about in each level how many maximum number of nodes. So here you can see that level 1 only one node is there, but level 2 we have 2 nodes are there, and level 3 we have 4 nodes. So based on this equation we are getting it. What is the equation? Level 1 it is 2 raised to I minus 1, ith level. So I is 1 here, so you will get 2 raised to I minus 1, that is 2 raised to 1 minus 1, 2 raised to 0, 1. So 1 node. And this is second level, 2 raised to 2 minus 1. So it is 2 raised to 1, 2 nodes. And what about third level? Third level maximum number of node is 4. How will I get it? Third level equation is 2 raised to 3 minus 1. So 2 raised to 2, it is 4 nodes. So next is total number of nodes in a binary tree of depth k or level k is 2 raised to k minus 1. So here equation is the minus 1 is on the exponent here, and here minus 1 is not part of the exponent. So total number of node in a binary tree is 2 raised to k minus 1. So it is 2 raised to 3 minus 1, 8 minus 1, it is 7 nodes. Now another important property of a binary tree is here, that is leaf node. The number of leaf node is equal to number of nodes with degree 2 plus 1. It's an important property. As per this property, it is saying that number of leaf node is equal to number of nodes with degree 2 plus 1. So the definition is, or the theorem is, for any non-empty binary tree, if n0 is the number of leaf nodes and n2 is the number of nodes with degree 2, then I can say n0 is equal to n2 plus 1. So before moving on to the proof, we will directly go an example. So here you can see the number of leaf node is equal to how much? 1. And number of nodes with degree 2 is what? 0. No node with degree 2 is there. So total number of leaf node is equal to n2 plus 1, that is 0 plus 1 is equal to 1. And in this case, number of leaf node is how much? 1, 2, 3, 4, 5. 5 are there. Now according to the rule, number of nodes with degree 2 is A has 2 degree, B has 2 degree, C and D. So total is 4. So as per the property, n2 is 4, n2 plus 1, 4 plus 1, it is 5. So you can see here 1, 2, 3, 4, 5. Now how this is being proved is very simple, but it is very important too. Here we have to assume certain variables. Let n1 is the number of nodes of degree 1 and n is the total number of nodes. Since all the nodes in T are at most degree 2, that was already told, all the nodes will be either 0 degree, 1 degree or 2 degree. So I can directly say the number of node is equal to n0 plus n1 plus n2. n0 means nodes with degree 0, nodes with degree 1, nodes with degree 2. So total number of nodes will be with the category of these three only. So n0 plus n1 plus n2. Now another is, can see that each node will be having a branch towards it. So this particular node has a branch towards it, this particular node has a branch towards it, this leaf has a branch towards it, this leaf has a branch towards it, likewise, but only root doesn't have a branch towards it. Now next assumption is, let B, capital B is the number of branches, then total number of node is equal to, so these 6 nodes will be having branches, so B plus node. Now node is not having branches, so we have to consider that. So I can write it as n equal to B plus 1. Now all the branches stem from a node of degree 1 or 2. That is also correct. Degree 1 or 2 will be there for all the branches stem, that like each branch will be stem from, generated from a degree 2 node or degree 1 node. So that is why I can say that B equal to total number of branches equal to 1 degree node or 2 degree node. So based on this rule, I can write n equal to B plus 1. So B is this one, so n 1 and 1 plus 2 and 2 plus 1. So these two equations can be equated and you will get what n0 is equal to n2 plus 1. Now we will move on to another concept known as fully binary tree. It's very simple thing, we have already told about it. A fully binary tree of depth k is a binary tree of depth k having 2 raised to k minus 1 nodes. So whenever a binary tree is full, means all the nodes will be completed. fully it's available. Like if k depth or k level is there, we should have 2 raised to k minus 1 nodes. Then I can say that it is a fully binary tree. Here you can see it is up to this level 4, it is fully, all the nodes are available. So in this case you can see that 2 raised to 3 minus 1 nodes are there. So 7 nodes are there. That is why this level 3 or depth 3 tree is having full nodes available. At the same time, if you are considering this tree, here this node can have 2 children. So total number of nodes is only, here it is 5, but here it is 7. So as per the rule we should have 7 nodes, but here only 5 nodes are there. This is not a fully binary tree, but this is a complete binary tree. I will tell you why it is so. So definition of a complete binary tree is saying a binary tree with n nodes and depth k is complete if and only if it nodes corresponds to the nodes numbered 1 to n in fully binary tree of depth k. So here is a fully binary tree of depth k, like depth 1 to level, you can either say level, that would be better. 1 2 3 4 levels are there. So total number of fully binary tree, if you are representing, it will be numbered like this. So you will get 1 2 3 4 5 6 7 and up to 15. So it is numbered according to this. But in a complete binary tree, the same pattern of number will be there, but few nodes will be missing, right? So if all the nodes available in the complete binary tree has the same mapping of the numbered nodes, then this can be called as a complete binary tree. Next we have array representation of a binary tree. Array representation of a binary tree is very simple. Only thing is that parent will be, suppose the parent will be in ith position, the left subtree will be represented in 2ith position and right will be represented in 2i plus 1 position. So this is what array representation is talking about. Or if I wanted to know the child parent of it, 2 divided by 2, I will get the parent. So that is what, whatever the number that divided by 2, I will get the parent number. So here also 3 by 2, I will get 1. So left subtree for this parent I will be available in 2i. So 1 into 2. So second node will be, its left child will be available in the second index, and right nodes will be available in the 1 into 2 plus 1. So third position. So this is what array representation. Here you can see that the same by using an example. Consider this tree. So here is left skewed tree. So A is in position 1. So I have stored A in an array. Position A is stored in first index. Now the left subtree of it can be stored only in 1 into 2 position. So array index 1 is I have stored this root, and then its left subtree will be available in the 2 into 1. So 2 into 1 is 2. Second position I can put what? B over there. So B is available here. Now B has only a left subtree. So where I can store only 2 position into 2. So it is 4th position only I can store what? C. And then what about its left subtree? So 4 into 2. That position only I can store the D. So 8th position you can see D here. Now consider this tree. In this tree you can see that A is in the parent is in first position, so it is available in first position. Now its left subtree can be stored in 1 into 2. So 2B is there. Now what about its right subtree? 1 into 2 plus 1, that is 3. So 3 position C is stored. Now what about the left child of B? So B is in second position. Now 2 into 2 is 4. Fourth position I can store what? D. Okay. And then where I will store E, because this is the right child of B. B is in position 2. 2 into 2 plus 1. So in fifth position I can store E. It goes on. So this is what array representation of a binary tree. Now we can have linked representation of a binary tree. So it is something like this. We have a data here and we have a left child, we have a right child. So this can be easily represented by using a class like this. We can have a class tree node in which integer or character depends on the data. Here I have used integer, the data, and left subtree will be of type of what? Tree node, because each node will be having what? A node, left node. So in a binary tree, each node will be represented as what? This is what the node is. Each will be having a data field and it has a left child field and a right child field. So this is what the node representation. So this can be represented here, the tree node, the data field is integer data and it has 2 pointers for left subchild and right child. So that pointer will be of tree node type, tree node star left child and tree node star right child. Now whenever you are creating a class tree, you can either make it as a public or you can inherit this tree node into that class. So this is what a linked representation of a binary tree. So whenever if you are comparing two binary tree representations, array and a linked representation, array representation determining the location of the parent, where it is the left child, where the right child will be easy, and linked representation identifying what is the parent and left and right child will be difficult. But at the same time, array representation space overhead is too much, because if it is a left skewed tree, we have already seen a few spaces are vacant over there, and linked representation space overhead is very little. Okay, so next we will continue it in the next